Okay, good afternoon, everyone. My name is Javier, and today I'm going to present an inverse modeling framework built in FEniCS for characterizing complex physical phenomena in inkjet printing. So what do I mean by inkjet printing? Because this is not the typical printers that you might have in the office. This is industrial inkjet printing. So we are talking about being able of jetting very small amounts of material at a very specific position. And we use this for printing semiconductors, bioprinting, printing textiles, and so on. So essentially, this is a sketch of a printhead, and what we have is flow coming from one of the ports through a channel towards another outlet port. And in the sides of these microchannels, we have piezoelectric actuators. These deform when we apply a voltage to them, and this deformation induces pressure waves that propagate within the microchannels and form a droplet at the nozzle. The main objectives of inkjet printheads manufacturers are increasing jetting frequency. We are talking about 10,000 droplets per second. We want to push it further while maintaining the droplet reproducibility, meaning that we want to have the same droplet at every ejection, same volume, same shape. However, this comes with several challenges, and some of them are the residual reverberations. So these waves that were used to form the droplet also propagate within the channel until the viscous dissipation dissipates them in a long time. Another important challenge is modeling the internal printhead dynamics. We cannot place internal microphones or whatever, so this is very challenging, and this is the topic of the presentation. So how I'm going to solve this problem? So essentially, on one side, we have the experimental data, which is performed using Laser Doppler Vibrometry. I will show later how the data set looks like, but we are going to collect some data, and we are going to formulate a physics-based model for the flow inside the printhead. By solving an inverse problem, which is a data simulation problem, accelerated with the adjoint method, we will be able to find the key physical parameters of the system that make the model prediction fit in the data with remarkable accuracy. So let's have a look at the data set, essentially. So this is a slide of the printhead, and actually it's formed by many channels that are separated by these thin walls that are compliant, okay? So these walls also act as the actuators. So when we activate one of the channels, say channel 1, while remaining the rest inactive, and measuring the motion of the meniscus at the different nozzles, at different positions, we observe that not only the active channel is affected, but also the adjacent ones. So this is the way that a crosstalk manifests. What happens in channel 1 affects channel 2, 3, and so on. And this is undesirable. Good, so the formulation of the problem, as I said before, is an inverse problem in which we are going to minimize a cost functional subjected to the physics. And the physics is the equations of motions of these mechanical reverberations, the acoustic waves propagating and getting dissipated through the fluid. And we are going to model the actuators in two different ways. So the external actuator, the one on top and bottom, we are going to model as a Dirichlet boundary condition in velocity, whereas the actuators that sit on the interfaces separating different microchannels, we will impose continuity of acoustic velocity and continuity of stress. And we will add this jump in stress that is one of our unknowns. The cost function we want to minimize is essentially data model discrepancy. If this distance is small, it means that our model fits the data with high accuracy. And we add some regularization to ensure that we satisfy some industrial engineering constraints, okay? The unknowns that are parameters important for the industry will be these boundary conditions or jump in acoustic stress. So we will find this from the data. This is how the data set looks like. So I'm showing how the meniscus, essentially the velocity of the meniscus over time at nozzle 1, the active one, 2, 3, 4, and so on. So we see that nozzle 1, the active one, has the meniscus is vibrating, but we will see that the magnitude in nozzle 2, 3, and 4, which are the passive ones, also this magnitude is non-negligible, okay? After we solve this optimization problem and we find the model parameters, we find a model prediction that fits the data with accuracy over the whole data set. Okay, apart from fitting the data, we can also reconstruct the internal printhead dynamics. And this is very important because industry cannot do it with experiments. The experiment just gives us information about the external flow, not the internal one. So what I show here is a portion of this printhead, and black lines are the actuators separating the 4 microchannels. And when I run the simulation, you see that this is the crosstalk, okay? Waves are getting propagated between microchannels, affecting the dynamics in the adjacent channels. And we can also quantify 3 sources of crosstalk. So the first one and most obvious one is direct crosstalk, because the actuators are separating multiple microchannels. When the actuators induces positive waves in one channel, it will induce negative pressure waves in the other channel, okay? Then we have crosstalk. I will play it again. We have also crosstalk. We also have crosstalk through the common ink manifold. So waves go from the microchannels to this manifold, and from this manifold to the other microchannels. And finally, we can also quantify crosstalk from the printhead structure. Okay. Apart from this, we can now show what are the inferred parameters that we found during the optimization problem, and we can say something. So if we look at the total stress jump, the jump in total stress and acoustic velocity at the active actuator, we actually see that the actuator is kind of behaving like an underdamped oscillator. In actuator 2 and 3, which are passive, we kind of see similar behavior, but there is more complex dynamics happening, especially at the early and later stages. And this is suggesting some coupling between the deformation of the passive actuators with the active actuator, which is actually important. Another important thing of this approach, and because we have learned physics, we can now extrapolate to other unseen printheads. All I have shown here is a dataset from a single printhead, and now this company gave me a dataset for another printhead. Using the physics that I learned from printhead 1, I was able to predict the dynamics in this printhead, okay, without the need of retraining the full algorithm. Good, so essentially the conclusion we'll say is I have developed this inverse modeling framework applied to inkjet printing that give us important insights into crosstalk mechanisms that are partially understood. We can reconstruct the internal dynamics and understand these physical mechanisms and also quantify them. And the most important thing is that using this information now, we can reduce by an order of magnitude the number of trial and error experimental campaigns. This industry so far relies on this, like trial and error. They change some parameters and then this needs to be repeated every time. With this inverse modeling framework, you kind of reduce a big chunk of it. And that's it. Thank you very much. Any questions?
Any questions for Javier? Yes.
Question. Very nice, but I'm curious. Can
Yeah, and actually that's my PhD thesis was on that. I also, it is published. I haven't shown the paper here, but I use adjoint optimization for finding the optimal way of moving this actuator so that you suppress these reverberations within an amount of time that you want. And basically this increases the jetting frequency. Yeah, that's, I can show you later the paper where I solved that problem exactly. Thank you.
So what you care about is presumably what comes out of the printhead. So if the actuators are not moving much, there's just the meniscus goes up and down and nothing happens.
Yeah.
So is that part of it?
Yeah. So there is a reason for that. Like you could model the full droplet generation process, okay? Right. This is a very complicated thing, but it's doable. But actually, there are experimental data that show that once the droplet is ejected, there is a very thin with high surface filament that retracts back to the printhead very quickly. So, or
maybe it breaks up.
Yeah, or maybe you get satellites.
There's a lot of data on ordinary inkjet printing of this type.
Exactly. What is important is that right after that, and very soon after that, you get a meniscus rounded shape. And this is kind of the starting point of my simulation, which is a reasonable starting point if you think about it, because you essentially, that's how, after jetting the droplet, this is what you have, essentially. So you don't need to simulate the full printing, the full ejection process. Will be.
But what people have, and they found that it gets very complicated, and sometimes you get multiple satellite droplets which you don't want.
Yeah.
And so forth.
Yeah, I mean, it's, I know a lot of people working on this. This is just a way of understanding crosstalk, right? The purpose is to understand what happens inside, not what is happening outside, because what happens outside, you can put a camera and analyze it. But what happens inside, I'm not saying you don't need it. It will be cool if you have it, but maybe it doesn't give you that much extra information.
So would you recommend completely redesigning the printer so there's less crosstalk to begin with?
Yeah, so my first work was on an isolated channel where I was using the actuators for controlling the reverberations. But now with this model that I show here, it's accurate. I can use the actuators to minimize crosstalk. And this is what I'm working on now, essentially. So, yeah, thank you.
All right, maybe we have time for a few more questions. If not, then let's thank the speaker again. Now, our next speaker is Louis Gombert. Is that correct?